Welcome to part 5, Generalized Logistic Function. So the first results from our basic logistic function do not look very good. If we take a look back at the data from Italy, we trained our model up to May 1st and then predicted from May 1st onward. So we can see the orange line is very flat compared to what actually happened in blue. So the issue with the basic formulation of the logistic model is that it does not allow for asymmetry. So the current logistic function is symmetrical around its midpoint. So the left side of the graph has to match exactly the right side of the graph. So the time it takes to go from 0 to, say, the midpoint must equal the exact same time that it takes to go from the midpoint up into the upper asymptote. So in most areas, you'll find that the tail of the curve takes quite a bit longer to reach its asymptote than the beginning. So what happens is there's expedient growth up to the midpoint over here, and then it takes quite a bit longer to reach the asymptote over here above. So the current logistic function doesn't allow for that kind of asymmetry. So we're going to introduce a new function called the generalized logistic function. So it looks similar, but we're going to raise the denominator to 1 over v, and this parameter v is what will allow us to allow us to give some flexibility to the curve. So this new parameter has to be positive. So for values less than 1, what will happen is that the growth before the midpoint will be faster than the growth after, and this is typically what we're trying to achieve. So we want fast growth in the beginning and then kind of slow growth to the asymptote over here. It also happens to shift the graph to the right, so it does a horizontal shift as well. Now for values greater than 1, there'll be slow growth in the beginning and there'll be fast growth after the midpoint. So I'll show several examples of this so you can see exactly what's happening. All right, so let's go ahead and create a function. Just like we did before, we're going to add a new parameter v over here, and we will just add it to our function right here. It'll still be one line. Okay, so this function that I've created is going to show us the difference between values of v for less than 1 versus those greater than 1. Let's go ahead and just enter it in, and we'll plot so you can see what it does. So we're just creating a generalized logistic function with these inputs, and now we're going to put set v, this is the important parameter here, to less than 1. Here it's just going to be 0.1. So this has the effect of making the growth in the beginning take a shorter amount of time. So I put these horizontal black lines in here so you could see that, visually see where the growth is and how long it takes to get from the same amount of cases. So here from the case number 100 to 500 is less than the case number of the days it took to go from 500 to 900. You can see here, and I put the days over here, it took 25 days to go from 100 to 500 and 38 days to go from 500 to 900. So that's the case when v is less than 1. Now when we make v equal to 1, well, this will reduce the function back to its original form. So you put v equals 1 over here, 1 over 1 is just 1. So you're back to just the normal symmetrical logistic function. And we can see here it's perfectly symmetrical. The only reason the days are not exactly the same is because there's some rounding with respect to when did it actually cross 100 versus 900. But other than that, it actually is the exact same, and it is perfectly symmetrical. Now, you'll take notice that if you've noticed, x0, which still controls the left to right, the horizontal shift, is actually affected by the parameter v. So normally when we had x not equal to 0, the 0 would be where the midpoint is. Now you notice over here v equals 0.1, we still have x equals 0, but the midpoint, that is where the case number is halfway to its asymptote at 500, is no longer at 0. It looks like it's around here, so it's a little bit past 50 in this for this x values. Now, if we look back over here, this is reduced to original logistic function, and so the 0 mark, or the midpoint at 500 cases, is directly at 0, which is where you would expect. So this V not only controls the asymmetry, it does shift the graph left or right. So if it's less than 1, then it will shift it to the right. And if it's greater than 1, it'll shift it to the left. So I summarized it over here. Okay, so we have a case where V is less than 1. We have a case where V equals 1. And now we're going to look at a case where V equals or is greater than 1. And as you can see here, we just look at the summary over here. It took 70 days to go from 100 to 500 and only 51 days to go from 500 to 900. So there's faster growth after reaching the midpoint, and it has a long tail on the left side. You'll also notice, and I'll make one more graph here, you'll also notice that the total number of days is affected. So the total travel time from 100 to 900 here is much greater, 120 days versus what we began over here with V equals 0.1, which was 63 days. So not only does V affect the horizontal shift, but it affects like the growth rate as well. If you want the same number of days to go from 100 to 900, you actually have to increase K, the original growth rate, over here. And so you can see here I increased it to 0.1, and I've decreased the number of days that it took to go from 100 to 900 substantially. All right, so now that we have our new formula, our predict all function is we're just able to plug it into our plug in the data into our function, and we should be able to immediately determine whether or not we have a better model or not. Okay, so just the parameters again. We have one more parameter. So again, we have to set the bounds, Lmin and Lmax. So Lmin, we're just going to use the very last date for the upper asymptote. It's of course going to be greater than that, but that'll just set a lower bound. The upper bound is very hard to guess. We'll just guess something very large here. Now, X naught has changed considerably. So due to the V parameter, since it shifts it left to right, we will now allow X naught to be negative, which can shift it back to left, and or positive. So it's not going to just be where the midpoint is. It does not have the same meaning anymore, but it still shifts it left and right. So this will give it the model some leeway to move more horizontally left and right. V also allows it to shift left and right, but its main purpose is to control asymmetry. The growth rate is also affected by V, but we're going to leave that range the same. V, we allow it to go to some smaller number, less than 1, and also numbers greater than 1 to change these asymmetry in case it needs a faster growth at the end. Okay, so here are our upper and lower bounds, and then we're just going to give it some initial starting value. We'll make the initial X naught of 0, and let's see how this one does. So now we look, and lo and behold, we have a very good fit. So it's only trained up until May 1st. So it only sees data up until May 1st. And then it's making a prediction on what it believes will happen in the future. And as we see here, the prediction is very good. It's almost exactly spot on. Now, we do have quite a bit of training here. We've seen most of the curve, and that makes it a little bit easier for the model. It's much more difficult to determine where the curve will land up in the beginning of a coronavirus outbreak. And so you'll have all sorts of models that can fly all over the place. But once you're this deep into the case wave, it becomes much easier to determine where it's going to go. Regardless of that fact, it still made a very good prediction. Now, here we can look at the final parameters. So it came up with about 237,000 cases as the final number. We have X naught is it's just this is negative 36 days. This is now acting as just a pure horizontal shift. The meaning is not easy to decipher because of the added value of V. Here's our new growth rate, and here is V. So this is quite a small number, so it means a longer tail. Okay, so have we built the perfect model? Are we going to get a perfect match and fit every single time? Well, no, this one is just a little bit easier to predict because we've seen most of the curve. If we shift the data back to May 15th, the stop date, the last date to March 15th, we've only seen just a small amount of the curve. And so when we use this, we can see that, well, it does trace, fairly well for the next, week or so, but then it just explodes to a much higher number. So it's very difficult to determine where a coronavirus case curve is going in the beginning of an outbreak. There's just a lot of variance and a lot of unknown. So just because it is a more sophisticated model does not mean we are going to be able to just perfectly predict the future. Okay, so I have a function over here that we look at just a few more countries, and this just automates that process. What the main thing that automates is just setting the bounds. So we're going to just pick very wide bounds for the lower and upper asymptotes, or the upper asymptote. So we'll just pick 1,000 times the last value, so extremely high upper bound. And then we'll just, as the initial starting value, we'll pick 5 times the minimum. Other than that, the other ones are actually going to be set in stone for their ranges. And then we're just going to predict all for these. So let's go ahead and execute this cell so we get that function in our namespace. So yeah, it's going to just be given all of the data. It's going to retrieve that country's coronavirus case curve, and then we're going to give it a start and end date. So we see we're using different countries, but we're also using different start and end points just to kind of see how the model fares. So here is United Kingdom, pretty early in its case wave. So you can see it, it follows the curve, but again, it's very difficult to predict. If you can predict, 45 days out, that's a tremendous model. So almost nobody is going to be able to build a model just with this little knowledge and be able to get it exactly right. Here is Belgium, a little bit higher on their curve, falls a little flat. Here is Germany. This one does better, but again, it's just sort of randomness, whether or not it gets it right. But it should get the general direction, and as long as more days, when more days come in, it gets better and better. So as we allow our data to model further and further, we should get better model. So you can even play around with this. We can say, all right, let's go all the way to, April 20th. Even then, it still falls a little short. It keeps on. This one has a very long tail, it looks like. So those are particularly hard to predict. The kind of very slow moving tails to the top. And here is South Korea, which had a very sharp turn, and also a long tail, and you can see that it's very difficult to make a prediction, but the general curve should be somewhat right, and for some curves you will get very good results. Okay, so that does it for the generalized logistic model. Up on deck is modeling new waves. So when there's multiple waves, how do we do that? Do we just use one curve? Do they affect each other? That's going to be coming up in the next chapter. But that is the introduction to the generalized logistic function.